Hello everyone. I would like to introduce a new CFD software, CFxD, for modeling flows. It has all the features required for full CFD analysis, such as geometry creation, mesh generation, setup, solution, and post-processing. The program is oriented toward engineers who may not have a deep knowledge of the CFD field, so the GUI has a straightforward, simple interface. Let's start with the interface explanation. At the top, we have the top menu. In the File menu, we have general options similar to other programs like New, Open, Save, Save As, Print, and Exit. Moving to operating conditions, you can set up the reference pressure for your simulation here. Please note that buoyancy is currently in development and will be enabled in a future update, unlocking the additional dialog boxes on screen. Additionally, the interface allows you to switch between SI and Imperial unit systems. Next is the Help and Logging tab. Here, all actions are saved in the log window. This tab allows you to see the CFxD status from the moment when we started the program, the license type, the initialized models, libraries, and more. In the Help menu, we have an integrated interactive manual where you can see all the available functions. You can call for the Help dialog box by pressing F1 on the keyboard when hovering over a button. For example, when you go to a line, it describes the pattern. As another example, if you go to the Create Edge Service button and click F1, you can call the Help menu. Finally, under About Program, you can check your license type and version. Now that we've covered the menus, let's look at how you'll actually move through a project. Below the main menu, we have the toolbar, which repeats the functions found in the File menu. After the toolbar, we have tabs for different features required for analysis: geometry, mesh, setup, solution, and result. When you finish a tab, the next tab will be activated. For example, once you finish the mesh tab, you must confirm you are done by pressing to mesh on the screen, and the next tab will activate. You cannot jump directly from geometry to results. All tabs follow a similar design: a left-hand menu, a central graphical view screen, and a view operations on the right side. On the bottom, we have a status bar. The bottom left shows hints, and the bottom right shows dimensions of the current geometry. The License tab shows your current level. Currently, we have Demo and Basic licenses. The Update button label indicates if the software is up to date. If a new version is issued on our server, this will change to a clickable button so you can run an update from here. Now that we have the basic menu covered, let's start a small project to show how it works, beginning with the Geometry tab. The workflow moves from 1D entities to 2D entities and then to 3D entities. Let's create points. For the first point, if the coordinates are 0, you can skip entry as it defaults to 0. Once created, it appears in the Geometry Entities list and highlighted in the viewer. You can rotate the view or use the Position View tool to reposition. Here we will input 10 meters for the x-axis to signify the length of the pipe. Next, we will do the diameter, which we will put in the y direction of 0.5. Now we select 3 points. Follow the hint, select center, a radius point, and then a height point to create a cylinder. Select the first point, the center, the second point, the radius point, and the third point, the length. Once created, the cylinder appears under the body name. You can hide the body, use transparency, or switch to wireframe to see inside. Rotation is controlled with the middle mouse button, and translation is controlled with the right mouse button. An important thing to note is you can import geometry via a step file, but here we are using natively made geometry. Let's name the faces of the pipe. We will call the first one Inlet. Call the naming function with the right button. The cursor will change to a cross, allowing you to select the face and enter Inlet in the dialog. On the right side, we will name the face Outlet. The remaining surface is Wall. We can skip naming it because any unnamed surfaces defaults to Wall, but let's name it Wall anyway. We have finished our geometry, a closed body with all names assigned. In the bottom right hand corner, you can see the geometry dimensions. Click the Mesh button to proceed. By default, the program will generate a recommended cell size, which you can refine if necessary. We have 5 levels of refinement. which applies by default to surfaces named wall. Wall treatment will generate prism layers. We can limit the generation time. By default, it is set to 600 seconds or 10 minutes. With the default number set, let's press mesh. The basic license is limited to 100 million cells, while the demo license allows 250,000 cells. If you exceed the limit, you will be notified. Below, we have mesh quality indicators. The green line represents a good mesh, followed by acceptable, low, and very low quality. To inspect the mesh, we have view settings and a scale option. We can also use cut options, for instance, a Y section to see inside. You may see some visual artifacts if the cells are not perfectly aligned with the cutting plane, but these are purely visual and do not affect the simulation. You may want to adjust your section, and you can do so by dragging the slider on the right side. Now for the Setup tab. Currently the program does not support transient simulation, so that is disabled. We will use steady with default iteration. We are modeling turbulent flow, though the program is capable of laminar flow as well. We will use default SST model, but the K-epsilon model is also available. Moreover, we are modeling an incompressible flow with a low Mach number. However, the program supports compressible flow up to 1 Mach. And we will not model heat in this example, so you can leave that option off. In the material library, solids are not yet implemented. For the fluid, we will keep the default properties for air. For the inlet, since we named it in the geometry stage, it is recognized automatically. We will set a velocity of 2 meters per second, define the turbulence length scale as 1 meter, matching our diameter. The outlet is set to ambient gauge pressure. The wall is set as a regular wall, though frictionless is an option. We will use one CPU core for this case, although parallel multi-core processing is supported. In the Solution tab, we have the convergence graph, monitoring graph, progress bar, and output data. We can monitor the mass flow rate imbalance here. For stability control, there are 3 numerical options: default, conservative, and aggressive. We will use default for this simple case. We will create a monitoring point at the center line, 1 meter upstream of the outlet. Next, we will select absolute velocity as our monitoring point by clicking with the left mouse button on the geometric entity. After this, simply press the Run button. The graphs are auto-scale, however, you can choose to zoom in if you'd like, but we'll leave it at the default auto-scale here. To verify the simulation is running correctly, you can see the monitoring graph on the left slowly converging to the bottom, and then the monitoring graph on the right converging to the center, stabilizing. There is also a progress bar, which is currently at 48%. With the simulation done, we switch to results. Let's create a chart at x equals 9. We'll set points at x equals 9 and y equals negative 0.5. The second point will be x equals 9 and x equals 0.5. In post entities, select velocity to see the profile along that line. Now let's create a contour plot. By default, a contour plot is created on the xy plane. Let's select the axial velocity. If you want a clearer view of the flow, you can toggle the visibility of the plane, the cylinder, or the line. We can see here that the flow is coming from the left. Here you can choose a vector plot by selecting a variable and then pressing the vector plot button. After creation, it'll be visible and you can hide the contour. Or if you'd like, you can add streamlines and take additional screenshots. Finally, click the Report button to generate an automatic PDF report. It includes statistics about the geometry, mesh quality, setup, settings, residual graphs, and your post-processing images as follows. That is a brief overview of CFxD. It's designed to be powerful yet accessible for every engineer. Thank you for watching.